Now, recall our phase diagram. Say we're existing on a phase boundary. We'd have a temperature and pressure saying we're existing on the phase boundary, but we need another property to help us define whether or not we are a liquid, a vapor, or a combination of both. Specific volume is a very useful quantity to help us determine our exact phase composition. Specific volume, denoted by the Greek variable nu, is our volume per unit mass of our substance. That is, our specific volume has units of meters cubed per kg. Under our continuum assumption, it is the mass per our smallest unit volume, such that our mass is uniformly distributed throughout. Density, or mass per unit volume, is the reciprocal of our specific volume. Rho is equal to 1 per nu. Now, these intensive properties allow us to construct our TV and PV diagrams. These diagrams are going to be very useful in describing phase transformation processes. Now let us look at an example of employing our formulation of specific volume and density. Say we have two tanks connected by a valve. The valve is initially closed. Tank 1 has a mass of 1 kilogram of air and a volume of 0.5 cubic meters. Tank 2 has a volume of 0.75 cubic meters, and the density of air within is 0.85 kilograms per cubic meter. When the valve is opened, time is allowed to progress such that the two tanks are in mechanical equilibrium. When the tanks reach thermodynamic equilibrium, we want to determine the final density and our final specific volume. To begin, we first have to list out our initial state variables. Tank 1 is going to represent state 1, that is, the properties of our air within the tank before the valve is opened. Our mass initially in tank 1 is 1 kilogram, and the volume of tank 1 is initially 0.5 cubic meters. Now we have to define tank 2 as state 2, that is, the properties of air within our tank before the valve is opened. The density of our air in tank 2 is 0.85 kilograms per cubic meter, and the volume of tank 2 is 0.75 cubic meters. When the valve is opened, the air is allowed to mix. Our final volume is going to be the sum of our two volumes, and our final mass is going to be the sum of our two masses. That is, our final density would be the sum of our two masses, m1 plus m2, per the sum of our volumes, v1 plus v2. We have all information except m2. Our mass at state 2 is determined by multiplying our density times our volume. Our density of 0.85 kilograms per cubic meter times our volume of 0.75 meters cubed gives us a mass of 0.6375 kilograms. Thus, our final density is our total mass, 1.6375 kilograms, per our total volume, 1.25 meters cubed. And this is 1.31 kilograms per cubic meter. Or we can say our final specific volume, which is 1 per our final density, is 0.76 meters cubed per kg. Lastly, we have to talk about the conservation of mass for a closed system. The conservation of mass, also known as our continuity equation, states that mass can neither be created nor destroyed. That is, the mass of our system must remain constant over time. If we have a closed system, i.e. a control mass, the mass within our system cannot change, regardless of the changes of time or volume. That is, the time rate of change of mass would be equal to the time rate of change of the integral of our density with respect to volume, and this has to be equal to 0. Now for an open system, things are different. The continuity equation for an open system states that the time rate of change of mass within our system has to be equal to mass flow in less our mass flow out. M dot represents a mass flow rate, kilograms per second. Now, a positive value of the time rate of change of mass indicates that our system is accumulating mass. That is, our system is gaining more mass as time goes on. A negative value of the time rate of change of mass indicates that our system is dissipating mass. Now, if our time rate of change of mass is equal to 0, that means our mass flow into our system is identically equal to our mass flow out of our system.